Ahead and get started. Thank you all for coming. So a little bit about me. I'm Daniel. I'm a data scientist at Endgame, mainly focused on malware classification and model evaluation. If you were here at the 2 o'clock session on this track, my colleague Phil Roth presented Ember. That's the sort of stuff that I usually deal with. So about this talk, we're going to be talking about de-obfuscating PowerShell with the help of machine learning. So that's going to be fun. A little bit of motivation to get us started. As we heard in the keynote today, there's this trend about living off the land. PowerShell is a pretty powerful tool, and attackers tend to use that because they don't have to drop a binary on disk. AVs, both traditional and machine learning AVs, are pretty good these days, and they'll probably catch you if you drop something. But PowerShell, you can get a lot of stuff done without actually putting anything. You can do it all in memory. Fortunately, PowerShell commands can be logged, and sometimes files are left behind. PS scripts are left behind. So security investigators like this because they can inspect them to see what the attacker was up to. Of course, attackers don't like making things easy. So a common technique is to obfuscate and encode these commands just so it makes it that much harder for an investigator. So a little warning before we get started. I'm not a PowerShell expert, and I don't use it in my day-to-day research or development. So I know what you're thinking. Great start. But I'm going to tell you why that's not a problem. I'm framing this as just a text analysis problem. And we'll discuss why. The valid question would be, why not just re-implement the PowerShell interpreter logic? That's perfectly cool. Somebody can do that, and it'll probably end up with a very clean solution. At the end of the talk, I'll talk about something that cannot be done by any interpreter. But that would be a pretty clean solution. However, I'm a sloppy data scientist, and that doesn't sound any fun to me. That's somebody else's job. Also, that only solves one obfuscation problem, and I like to work with ambiguity and uncertainty for the sake of generalization. The logic specific to PowerShell deobfuscation in this talk, or de-encoding, this can be swapped out for other obfuscation use cases, and it might still work for those. And the methods and processes used here all are the same. So you can have one tool to deobfuscate JavaScript, PowerShell, command line statements, anything else you want. So real quick, we're going to discuss the problem just a little bit. We're going to discuss what is obfuscation and encoding. Most of you probably know, but just a quick refresher. And then we're going to discuss how we want to solve this. And it's going to be in a couple steps. First, we're going to look at a file status classifier, a de-encoder, a deobfuscator, and then a cleanup network. Then we're going to go over some results. So obfuscation, generally speaking, it's using the functions and quirks of a language to create a command that's easily machine readable, but much harder to recognize by human eyes. So if you can't analyze it if you can't read it. Some examples of this, random case changes, just flipping the case on every character in a string, concatenating, or in this case, unconcatenating, breaking apart a string, just adding some plus signs, and the interpreter squashes them all back together. Reordering stuff. This is really gnarly when you have to read it. This is usually used when you have a bunch of variables that you just want to insert into a statement. For obfuscation's sake, it's used to break up strings and reorder them around. Backtick is a line continuation character. So what happens when you have a line continuation in the middle of a line? Well, the line just continues and it ignores the character. The only purpose that I've seen so far is if that's at the end of the line, it says, okay, keep on processing the next one. There are a bunch of others, splatting, white space, all that sort of stuff. And then there's variable replacement. If you just define a variable, a random variable as a string at the beginning of your file, then you can replace it all throughout the function, and it makes it really hard to read. So I apologize throughout this for trying to put full files up in a presentation. It's a little hard to read. But this is an example of just a regular PowerShell script before obfuscation. You can see it's defining some variables, it's doing a chocolatey thing, it has a try-catch in there, all normal stuff. So after obfuscation, it looks a little bit messed up. You could do this by hand and reverse everything, and that'd be fine. You could read it, but yeah, that's what computers are for, right? And just for reference, all these tricks are really well done by Daniel Bohannon. You should check out Invoke Obfuscation. It's a PowerShell module. I'm using that for both the obfuscation and encoding processes and throughout this project. Next we're with encoding. And so everybody probably knows this as well, but it's a glyph or character level mapping into another encoding scheme. So the glyph A, capital A, translates to 41 in hex or 65 in decimal. Left bracket is 5B in hex, 91 in decimal, so on. For the sake of this project, I'm only considering hex and decimal just to show that this works with multiple things. It's easily extendable to more schemes. I just got lazy and didn't want to write the de-encoding for everything. So this is an example of a file that is like encoded with decimal. So you can see all the characters there in the 0 to 256 range, just a list of them, and you can see some of the logic in PowerShell to put it back together. The for each int as character casts them all as characters and then joins them at the end. Similarly, you can see this something in hex, same sort of deal. You convert all to N16 and join, all that sort of stuff. So that's just what, I mean, if you're looking at this, you're obviously not going to see anything. It's encoded. But you can de-encode it pretty easily. So now we want to see how to build something to take any file, whether it's encoded, obfuscated, not obfuscated, anything, and then output the result that is non-obfuscated. So to do that, it's helpful to know what you're actually looking at. So for that, to that end, we're going to build a file status classifier. So I know a lot of people here might not be as read up on machine learning. So we're going to do a couple real quick intros into some topics as we go along. So what is a classifier? It's a machine learning approach for predicting the category of unlabeled samples. So you have input. In this example, you'd have a PowerShell script file. You throw it through a feature generator, and it, turns and then spits out all the sort of characteristics that you think are important. Then throw it into this black box classifier, and it predicts this output, either hex encoded, decimal encoded, obfuscated, non-obfuscated, whatever your output classes are. And so let's say we have this classifier and it works well. The next step would be if we have a classifier and it says it's encoded, we run it through a de-encoder and then run it back to the file status classifier because it could be obfuscated and then encoded or any combination. Similarly, if we determine that it's obfuscated, we run it through a deobfuscator, back to file status classifier. And finally, if we ever determine that it's non-obfuscated, we output the results. So pretty simple logic of returning it back and then keep on working until you get the result that you want. So for building a classifier, the typical machine learning approach is to, there's three parts. One, gather a lot of samples with labels. And by that, I mean a lot of PowerShell files with the tag, is this obfuscated? Is this hexadecimal encoded? Is this non-obfuscated? And then for each of those, you want to generate features on those samples and then train using your selected algorithm. So stepping through that, let's talk about samples. This is often the hardest part of any data science problem is getting the right samples. If a couple options for you is if you have access to VirusTotal downloads or a similar service, you can grab that. You can scrape GitHub, or you could ask your friends for all their scripts. We're going to be having to train on tens of thousands of scripts, so you might need to make some more friends if you do that approach. Luckily, since we're using invoke obfuscation, once we have just regular PowerShell scripts, we can generate the encoded and the obfuscated versions of those, so we get the labels for free. So features, classical machine learning, logistic regression, support vector machine, some others that you might have heard of. You basically hand define all the features that you want. You're going to write a little script that defines the number of characters, the number of values, the entropy of the file, the number of backtick marks, all that sort of stuff. Personally, I find that pretty annoying to derive all these yourself. You're going to miss a bunch of important ones. You're going to spend a lot of your time doing feature engineering. It's just not very fun. And it often, for text, it often doesn't represent the relationship between characters well. If you have just the string user, USER, it's going to have the same or very similar results as if you reverse the string, RESU. So that, the sort of relationships between characters in this case is probably very important. So classical machine learning isn't really going to work for us. So we're going to try to use a neural network. And super brief, because we don't have time to go into a lot of this stuff, this is just a classic example of a dense feed-forward network. You have your input values on the left. Each of these circles are nodes that have activations that propagate through to the next layer. And then you have an output layer that defines your classes, the output classes like hex or decimal or obfuscated. So if you're running a sample through this while training, you take your feature or you take your sample, throw it through the input layer, it propagates through and then makes a prediction at the end. If your prediction's right, that's awesome. If it's not, then it back propagates and changes the activation of all of the nodes throughout the network and then tries again with other samples. Eventually, with thousands, tens of thousands of samples, lots of training, you're going to get a whole bunch of awesomes and you have a good classifier. What we're actually going to be using, though, is a special type of network called a LSTM. So you're asking, what is an LSTM? And with all definitions, we go to Wikipedia. Long short-term memory units are a building unit for layers of a recurrent neural network composed of a cell, an input gate, an output gate, and a forget gate. All right, that's not very helpful. Maybe it's because we don't know what an RNN is. A recurrent neural network is a class of artificial neural networks where connections between units form a directed graph along a sequence. Okay, Wikipedia has failed us. A quick, short summary in more natural language. RNN is a type of neural network that keeps a memory. It can reference the previous states, the previous predictions that it made, as well as current input to determine the value. At the bottom in the notes, there's a really good blog on this. I think if you query LSTM on Google, this is the first pop-up, so that should be pretty easy to find. So this is the architecture of an RNN. You can see the input, on the left side, you can see the input at time t comes down, and you have this memory node which can reference its previous self, and then your output node, which is the prediction. So if you sort of unpack this from time 0 moving forward, you can see the first one, the memory node doesn't really do much. You have the input and output, but going on, you start to reference the memory node, so you reference the previous states as you're predicting. So this sort of does character by character predictions, referencing the previously predicted character. So that's pretty cool. And an LSTM, a long short-term memory network, is a version of an RNN that has some bonus internal network structures that let them handle long-term memory better than a standard RNN. Again, we don't really have a lot of time to go over that, so we're just going to leave a little star there to say it's special. So all those memory nodes have some little extra logic. That's where the forget gate, the input gate, all that stuff in that definition come in. Now, that sounds a little intimidating, and if you don't work with neural networks, they do look intimidating from the outside. But there are a lot of high-level neural network frameworks like Keras that make this super easy. So training this network, this is literally the code to do it. It's 9 lines, and one of those doesn't even need to be there. And it's a pretty simple classifier on 10,000 samples per class, so 40,000 samples. You can run this in under 30 minutes on a CPU. So if you're worried about it, don't be. Just try something out. Computer science is always about its abstraction, so you don't have to know exactly how LSTM works if you know what sort of problems it's good at solving. Now we're going to look at how we're going to build a decoder. So now we've got a file status classifier that's pretty good. That one that I trained is well over 99% accurate, and it's not really a big deal. So now we're going to look at de-encoding. So I could have just figured out how to use PowerShell's interpreter or the interpreter logic to decode a file like this. You can see how it should be done, basically. But like I said, I'm a sloppy data scientist, and I see a pattern. And you know what's really good for patterns? Regex. So in 4 lines, you can decode that whole thing. Just by finding all the things that fit that pattern, casting them as characters, and then joining them all back together. So that's pretty easy. To be fair, hex is a little different because it has a different inline structure, or end of line structure. And there are some other things that invoke obfuscation does, like creating split variables that can make this harder, but that's adding 5 or 10 lines of code, so it's not really too bad. And in life, my pro tip is don't do anything too complicated when there's a simple answer. All right, so de-obfuscation. This is a fun one. The bulk majority of this stuff can be handled by logic. You can concat strings together, you can remove backticks, you can replace variables. Some are really easy. Removing ticks, just replace every backtick except for the one at the end, if there is one. Splatting, just look for something that looks like a splatting and replace it. For string assignments, you can cast things as strings or characters and all this sort of stuff. You can find a match and just replace it pretty easily. None of those are bad. They're all completely reversible functions. Sometimes it gets a little bit more complicated. The reordering thing that I talked about, where you have all the braced numbers and then -f and then a bunch of strings that get reordered. To do that, I found the best way was to do character-by-character processing to find that hook, -f or -F, then find all the placeholders before it, find all the strings and valid non-string values after it, replace them, then iterate. Because you can do this on multiple times on a line, and it just looks super gross. But there are multiple different ways to do this, too. You can do replace, invoke, and a couple other things like that. But it's a finite list. These are all definitely solvable. And I think I enumerated most of them in the code, but maybe not hit all of them, but it's definitely a solvable problem. So we have a dozen or so of these little fixes to match all the stuff that's in invoke obfuscation. So let's see how we do. First, we look back at that file that was obfuscated. Looks gross, good times. And then after applying it, it looks a lot better. It's actually readable. There are some things that bug me a little bit. You see, the capitalization stuff, you're not going to fix that with logic. And that's mostly what happens there. So this mandatory false domain, for some reason that gets me. And I think it's because of this. The sort of mocking SpongeBob, always there, always mocking. So this is where things get sort of interesting. All the previous work that we did could be run backwards. They're all reversible functions, like I said. Random casing strings and variables, that's a different thing. So the thing is, if you're looking at this, if I'm looking at this, if you're looking at this, if anyone in this room is looking at this, I bet you could guess how that's supposed to be formatted. There are a couple different options, but you probably guessed one of these. You know the word module, you know the word directory. Through your experience and intuition, you can probably figure this out. So that's one thing where logic fails, but neural networks sometimes have an edge up. So this is where we actually put the toothpaste back in, as the subtitle goes. So we're going to try to train a neural network to learn the various casing formats using PowerShell. And as a bonus, it'll help out with some of the extraneous stuff that, since I'm a sloppy data scientist, I might have missed. So extra braces, extra quotation marks in some locations, all that sort of stuff. So if you liked LSTMs, you're going to love this, because this has 3 LSTMs in it. So the goal right here is to translate something like this variable module directory all messed up into variable module directory. And we're going to use a sequence-to-sequence network to do this. So what's a sequence-to-sequence? It's a type of neural network that's often used in machine translation. So think language translation, Cantonese to English sort of deal. So it uses LSTMs to create an encoder network to transform the starting text, and a decoder network to use the output and the decoder memory to predict the output. So think of the encoder network as a network that sort of understands Cantonese, and the decoder network is a network that understands English. And they're able to talk to each other in their sort of internal intermediary language, and then take characters as they come in Cantonese and convert them into sort of characters as they come in English. Also, this is way outside the scope, but Keras has a nice blog on this. And a lot of the code used in this is very similar to the example code in Keras's GitHub. So I initially tried to translate an entire line. I got a little overzealous, and I was like, we're going to do entire lines at once. Machines are going to take over. It's going to be great. So we start with this messed up global stored AWS region sort of string or line. And it started well. It started out. It's predicting line or character by character, and it got to global and the colon, and then, oh no, it got user, and remember, it's using the previous predictions to predict the next one, so it just really goes off the rails. I don't know if that's valid or not. It'd be interesting to see what actually happens there. So I decided to downgrade the scope a little bit, and so pick words in each line to consider. So we're trying to find the corresponding word in an obfuscated and non-obfuscated file. So like, if before we just looked at store AWS region as a word, or just AWS region as a word, and then try to match that messed up version to the original version that's not messed up. So the method I'm using grabs most of the variables and other EC obfuscated stuff, and so you use the obfuscated word as the input and the non-obfuscated word as the desired output during training. And so it predicts character by character to get the new input data. It still has some quirks. So this get local membership turned into get lock mirfilation. As an aside, I actually doubled the training data and doubled the training time, and this works perfectly now, but I thought I'd leave it in because it was funny. But in general, it performs very well. So this sort of messed up local group turns into properly capitalized, vagrants, all lowercase, PS bound parameters is the right casing. All that's good. So now we've done four things. We have a file status classifier, we have a de-encoder, we have a deobfuscator, and we have a cleanup network. So let's give it a shot. We have original file, this thing, proper PowerShell, obfuscated, encoded, and then what we're going to do is we're going to run it through and check, and we're going to do all these steps. So initially we check the status. If it determines it's encoded, runs it through the de-encoder, returns it back to the status checker. If it determines it's obfuscated, it deobfuscates it, runs it back through the status checker. If it determines it's non-obfuscated, then it outputs the file. And so if it deobfuscates something, it's going to return a partially fixed, so that's just with the deobfuscation logic, and then the fully fixed version with the cleanup network applied as well. So we're going to see the partially fixed version. You know, we saw that before. That was pretty cool. And then the cleaned up version. So all those things, almost all those things got fixed. Now, there's still some work to do. You can see the SR number on line 4. That one didn't quite get picked up, and user handle near the bottom. That one didn't quite get picked up. But this is trained on 30,000 samples, with their various encodings and obfuscations, which, as far as neural networks go, is not a lot. So this has a lot of room to improve. But it pretty much works. So some notes about this as we do a little recap. The output is not necessarily a valid PowerShell. There are certain things I can see that it's going to break this. They're unbalanced parentheses. There's an extra period in there somewhere. Some stuff like that. But this is for investigators to look at, not to run. I still think I'm going to be able to get this to work where it produces valid PowerShell at the end. There's just a little bit more to do. And as a note about machine learning in general and the cleanup network in specific, there's a chance that it's overtraining a little bit and doing some memorization. This is a problem with, like I said, machine learning, especially with neural networks. But for the purpose of this, I'm going to argue that that's sort of a difference without a distinction. If it's learning how to handle random cased variables and then output a correctly cased variable that it memorized sort of fits with that pattern, though that's solving the same problem that we were outset to do. So it works. That might end up having an upper bound as a 90% solution because it won't be able to do much with variables that it's never seen a sample of before, versus a 95% solution if it was learning proper case. We're going to have to do a lot of introspection and a deep dive to determine if it's memorizing or not, because, neural networks and stuff. Fun. And back to one of my original points, since I said I like to work with ambiguity and uncertainty for the sake of generalization, only 3 things here are specific to PowerShell. 1, the samples. For the file status classifier and for the cleanup network, if you're going to do this in another language, you're going to need samples in that language. Fortunately, there is something in neural networks called transfer learning, where if you sort of bake in training on something, you can train the last little bit with the new samples, far fewer samples than you had, and it'll learn that. That's because a lot of the internal structure of the network is learning just how to process text, how to make relationships, and it's just the ends that you're going to be fixing up. Also, the de-encoding logic. I wrote this with a PowerShell example, but it's all a regex thing, so it might work with another language without change. Probably it's going to need a tweak or two, but that's easy to do. and the deobfuscation logic. Each language is going to have their quirks, how they handle obfuscation. But the way this is built, you can make a little quick define, add it to a config file, and run that. So it's really easy to just add stuff to this. Unfortunately, today, I'm not going to have a tool or code to release, mostly because I was fixing it on the plane last night, and it's not quite clean enough to come out. But we're going to have a blog in a couple weeks with a lot more details and a release there. And that's all I got for a talk. Happy to take any questions. I know we're right at time, so if anyone wants to do after or here, I'm good to go.